From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
So I'm in this kind of background today because I've always had a very strong interest in science fiction, space exploration. I love Star Wars and Star Trek and Battlestar Galactica when I was a kid, and then later on Babylon 5, and now things like The Expanse, which this background is from. And so I'm so pleased to be able to take part in space exploration in my own way on the additive manufacturing side.
That was Eliana Fu. Eliana is an industry manager of aerospace and medical at the Trumpf Laser Technology Center. She was educated at Imperial College, University of London, with a master's degree and PhD in material science. After working extensively in the traditional manufacturing world with TWI, then TIMET and SpaceX, she turned her attention to additive manufacturing at SpaceX and then with Relativity Space as senior engineer for additive technologies. She also serves as Women in 3D Printing Ambassador for Las Vegas and is a recipient of the TCT Women in 3D Printing Award for 2022. Before we get started, head over to www.3degrees company and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials, qualification, or general additive manufacturing support, reach out to the team through our website or via email at info@3degreescompany.com. All right. Hi, Eliana. Thank you so much for joining the show today. Excited for the conversation. And so like we do with all our guests, I like to start at the beginning. So where were you born, where you grew up, kind of what got you on those kind of stepping stones into a career in manufacturing?
Well, hi, Mike. It's so great to be on your show. I've seen so many people on the podcast, and I'm very honored that you also asked me to come on. My role I'm currently at Trumpf as industry manager for aerospace and medical. And I've been in AM, additive manufacturing, for about 10 years, but my path there is pretty unusual. I was born and grew up in London, in UK, and I did master's and PhD Imperial College, all traditional metallurgy. So titanium is like my background, and I really didn't know anything better than the usual sort of forging, casting, sheet metal type of world. That's kind of what I grew up with. I mean, I spent time working in Sheffield, UK, which is the home of stainless steel, and that's really all I knew for like my whole life. And I was working at the titanium company TIMET here in Henderson, Nevada, and I worked at that company for 8 years. And what I noticed is more and more of the customers. So TIMET makes traditional. It by the way, is one of the biggest titanium producers in the world, certainly in the US. Traditional mill products, so that's sheet and plate, billet bar, forged product, ingot product, input stock for making wire, strip, coil, all that kind of stuff. And more of the customers were asking for input stock or feedstock for additive processes. And I was like, well, what is that? So they're asking for gas atomized powder and things like that. And we didn't make those at the time. So I just noticed more and more people asking for this. At the same time, I noticed that if you typed into a search box, just randomly searching careers, titanium forged product metallurgist, like the number of jobs available, I can count on one hand for the whole of North America. And if you typed in additive manufacturing engineer, there would be hundreds of jobs. And I was like, what is that? I should find out more about that. And so I made it kind of my task to educate myself in that field. And then I realized, wow, this is like a completely complementary sort of field of study to traditional metalworking, but it uses many of the same principles. So you could say that metal AM especially is like the offspring of welding and casting, let's say. So some of those metallurgical principles are the same. They're just taking place on a micro scale, not taking place in a 10,000 pound ingot. And so, I really got into it when I got hired at SpaceX, who were one of my customers, and then later on at Relativity Space. So before I joined Trumpf, that was my last position. I was additive processes engineer at Relativity Space.
Awesome. So maybe let's rewind it even more. So like what was the first inspiration that got you interested in metallurgy? Was there like, did you know someone that was a metallurgist? Did you just what was that kind of spark that got you down that track originally?
I actually didn't know anything about metallurgy or material science. And it wasn't until when I was in high school, someone sent me a flyer for one of the colleges in London. And it said, come and study material science. And it was a flyer with a picture of a tennis racket, a military aircraft, commercial aircraft, and like a golf club. And then it says, material science is what stuff is made out of. And I was like, a light bulb went off saying, ding, like, oh, why don't I study like what stuff is made out of? So that's where it came from. And the class did used to be called metallurgy, but as they expanded, it wasn't just metals, it's ceramics, polymers, biomaterials, and other things. So to be all encompassing and more inclusive, they call the field of study material science. Mm-hmm. And that's where what I like about that is if you don't like metallics, let's say, you can do ceramics, or you can do polymers, or you can combine several different disciplines. You can be on the physical metallurgy side, or you can be on the computational sort of modeling side. And so all these different things you can study within the branch field of material science. And that's what I really like about it. And it was only really years later that I realized additive manufacturing comes from that. And that's what really sparked the imagination.
What was it about kind of the metal side versus biomaterials or electronic materials that caught your eye?
I don't really know. I think it was maybe metallics have this impression of being, really strong, and that's something you can make your spacecraft out of. I was a huge fan of like Star Wars and Star Trek and stuff like that when I was growing up, and then later I was really interested in stuff like Babylon 5 and Battlestar Galactica and stuff like that. So like things like living on other worlds or exploring our galaxy and stuff. I mean, you couldn't do that without metallic. So I think the first step is just learning to fly commercially before you fly to space. So that's really where I got that idea from. And then I guess during my master's, I zoned in on titanium. And then in my PhD, I just continued in titanium. And I just found that like when I discovered there were all these like different uses for it, and you can do so many things with it. It is like my favorite metallic of choice. And I'm not just saying that because I worked for a titanium company for 8 years, but if you think about it, it really has lots of attractive properties.
So one thing we haven't talked too much about on the podcast is like what is the role of a material supplier on the metal side? Like what were you doing kind of on a daily basis when you were working for like kind of providing metal to end users?
Yeah, amazingly, most metals come from the ground. They're usually found in nature in the form of an ore. There are very few that are found uncombined with other elements. So part of the company that I work for, TIMET, Titanium Metals, if you read a book called Black Sand, The History of Titanium, it actually tells you how we in the 20th century have been using titanium as a metal, an engineering material. And so part of that involves extraction from the ore in an industrial setting. So once you retrieve metal from its ore, in titanium, we use a carbochlorination process called the Kroll process. And then we mix in other materials like aluminium, vanadium, and so on. And that's how we get things like Ti-64, which are alloys. So the company that I work for produced these alloys, but it's all very well to make these giant ingots. You can't make a fan blade out of that. So you have to do further processing to these ingots. And so you would make them into the form of bar, you would roll them into plate, you would sell those to other people. So those other people would be people like forging houses or casting houses, and they would take that input stock and make those into fan blades or fan discs or sheet metal for, you know, other sort of applications. So primarily in titanium, 75% of all titanium that's used industrially today is aerospace. And then the rest is like some oil and gas, some commercial, a lot of biomaterial actually, and some other decorative and cosmetic. But you know, what the sort of applications are basically corrosion resistance, light weighting as compared to other engineering materials like steels. So titanium has displaced a lot of those heavier steels in, let's say, turbine engines and things like that. And especially for aircraft, any drop of weight saving that you can get with any titanium process actually is going to help fuel economy and range on, especially on commercial aircraft. And military aircraft have the same kind of needs as well. So if you look in the history of, you know, material science and materials development, lots of things that we now take for granted, which is extended range on smaller, medium-sized aircraft like 737s and so on, are accomplished with the use of titanium. If you've ever flown on a Boeing 787, they did market that aircraft as the aircraft with the most amount of carbon fiber ever used, but they do not say, and this is actually true, that is also the most amount of titanium that's ever been used on such an aircraft. And that's because carbon fiber and titanium actually go together really well. So, but it wasn't something they used in marketing, which as a titanium person made me sad. But titanium is also used, by the way, for architecture. So if you've looked at the Van Gogh Museum in Amsterdam or the Guggenheim Museum in Bilbao, there's sheet metal surrounding those buildings, which is completely decorative, and it's all titanium sheet. So our company made all that sheet and someone else put it together.
And so you mentioned, as you were talking about some of your kind of later stops along your career at Relativity Space and SpaceX, that they were your customers. So talk about kind of that transition first, maybe as kind of what was your role in terms of like supporting customer development? I mean, like you're a titanium company, so are people coming to you with applications like, hey, does this make sense? Or can you get us this amount or this feedstock? What was kind of the day in the life like back then?
Yeah, totally. So my role was R&D services engineer. So I basically, you know, on the website, there's like a whole bunch of data that you can download and say descriptions of this alloy or that alloy. And then it says, ask us a question, and there'll be a free form text box, and you'd fill out the text box and then ask your question. Those questions came to me. So I got all the questions, whether they were legit questions or crazy questions, but I treated them all the same. I treated them like they were all deadly serious. And some of them were, you know, people just trying to learn a bit more about titanium. Some of them were people who wanted information and didn't know how to go through the usual route. So I would get some of those problems. Sometimes we'd have direct customer problems where they'd ask a question like, why does my sheet do this? Or why does, you know, my billet do that? And what's going on here? And, you know, can you tell me why this chemistry is like this? And what I found was people are very quick to make assumptions about how the materials process too much. And so it's your job as the person who sort of like translates that to the users. How did this material come about? What was the processing steps with it? And by the way, this also is highly applicable to additive. And what was the resultant, you know, microstructure or use or application of that material? How do defects come about? Why is it if I order this, I get that? Or if I order the material in a different format, I get something else? why do I choose one chemistry of titanium over another? And when I say chemistry, I mean chemical composition, not chemistry as such, because everybody knows chemistry is a branch of science. But that's just terminology. And so, not everybody went to school for 7 years and learned about titanium. So, there's lots of people that just kind of need walking through the process. And so if you just do that in a kind of logical and a way that they can easily understand, that helps a lot. So part of the other job that I had was actually going out to our customers and teaching a basic titanium 101 class. And so I did that at almost every single one of our customers. The only one I didn't give it at was Pratt & Whitney, because they already had someone teaching that class. But I went everywhere with that class. I went to Brazil, China, all over Europe, all over North America, and Japan. And that's basically what I learned is people want to learn about titanium. They don't know where it comes from. They want a helping hand to understand what it is that they're purchasing and what they're really getting into. And so as a result of that, that's how I came to teach that class at SpaceX. And then they kind of encouraged me to apply sometime later.
And so what was that like in terms of going from kind of the material supplier side to the end user? Kind of what was that?
Yeah,
how was
that's a
that
great
transition?
question. Yeah, it's so different being on the other side of the supply chain. One thing that I learned is, well, because I'd only been working in titanium forever. And so when I got to SpaceX, they give me every metallic you could think of. So aluminium sheet, and then some Monel and nickel billet and things like that. And so, but to me, it's all the same, right? It's all material science. It's all metallurgy. It's the same. It's just a different composition. And so what the other thing that I realized was I'm dealing with the same people that I've been dealing with as just from the other side of the curtain, if you like. And then so that relationship was very interesting. People who used to be my customers when I was at the titanium company and now my suppliers when I'm at SpaceX. And so, you got to see the whole thing from a different lens. And I think it's great because you understand all the challenges that suppliers go through. Whereas when you're a customer, you're the one who's pounding on people. Where am I going to get my material? Why isn't it on my dock? Why isn't it in the condition that I want? And now every single thing that happens. So that level of understanding is really helpful.
Yeah, and I imagine too, as you are kind of, you've gone like you've sat in the shoes of material supplier. So when issues come up, when there are challenges, when things don't come exactly as you expected, you kind of know the right person to talk to or like how to translate it in a way.
The person to talk to or exactly the person to call or email. We have them on speed dial, send them a text and say, hey, what's going on here? So that's another thing that I think is really helpful, the role of a quality engineer. If you can put that hat on so that you're approaching it from not just the manufacturing side, but the quality side as well, which is something that we don't think about, especially if you're a manufacturing engineer, because you just want it to take place, versus if you're a quality engineer and then you know that there are certain steps and things that have to go through and it doesn't happen overnight. But if you're a customer, you want those results fast and you want them accurate and you want them overnight or same day.
And that's especially the case with additive, as there's so many process variables even in the machine, but then kind of getting the right powder, getting the right feedstock, getting the right wire, or whatever it may be, and then all the next metallurgy steps that happens to actually make a part and do that repeatedly. And I think that is so interesting in the additive sense that we're still doing a lot of figuring out of what makes a quality part. How do you measure it? How do you document it? How do you do it repeatedly? And I think a lot of companies like the ones you've mentioned are really blazing a new path on that front.
Yeah, but I think it is important that we look at sort of standardization, qualification, certification as a community and not as a bunch of individuals. because I can see that there's benefit to working together collaboratively rather than trying to do everything yourself. For one thing, it's very expensive to do all that testing by yourself, and another thing is, do you really want to waste your time reinventing the wheel when someone else has already got these results? And so that's why, I think organizations like the ASTM F42 Committee on Additive are a lot faster.
Absolutely. And I think I joke with, we've had Element on the on the podcast before, doing a lot of that materials testing, and so they don't mind that Boeing and SpaceX and everyone and their brother sends them the same titanium dog bones every month to do some of the testing on, and it is one of those things where you're getting the same result over and over again, but it's just different walls and different names on the packages that you get this information from. And as organizations like you mentioned, ASTM and others are building that, I think it just unlocks that kind of first step that makes it so expensive for many companies to jump into the supply chain, if you have to go through and qualify each machine and each material every time.
Yeah, okay. So that is so I would say for the traditional manufacturing world, we already have that data. We have those thousands of data points over 75 plus years in publication like MMPDS. We already know that stuff. For AM, we don't know it, and people are generating it. But if we combine them, we would have several more thousand of those data points where we can a little bit more within, I don't know, some kind of error band, be comfortable that if we repeat this over and over and over again, we're going to get these results. Now, I don't think any two processes are quite the same, so maybe there's some scatter there, but certainly we are doing the work, we are generating it, so why not share that? And then people are going to say, because that's the way I maintain profitability. And of course, for a machine manufacturer, that's what they're trying to do at the end of the day, is to sell a machine. But actually, maybe the answer is you're trying to sell the solution to the customer's problem in the best way possible. And by sharing some of this data up front and being, a bit more open about it, that's where the collaboration that I'm talking about comes into. But that's also where we don't have to waste a lot of time, effort, energy, and money, let's say. I know no one likes talking about money, but it's an unfortunate part of life. But those things are expensive. And so, it's not just the cost of the tests, it's the cost of your time. Your time is valuable. You could be doing something else, or you could be investigating some other process, or finding out something a bit more interesting rather than going over the same bunch of data over and over again.
Absolutely. And so one of the things that, as we kind of fast forward in your career, you're at Trumpf now. We mentioned that at the beginning. So kind of going to the machine manufacturer side, when you were at kind of the end user side, kind of Relativity Space and SpaceX, were you doing a lot of DED work, or were you doing primarily laser powder bed fusion on titanium? Like, what was that transition into Trumpf? Like, where did the kind of connection happen on that front?
Yeah, so when I was at SpaceX, I did a lot of supplier quality actually on feedstock. So it was mostly a lot of powder investigation, and we did things like we surveyed powder suppliers in North America and stuff like that. At Relativity Space, because there are other AM processes besides powder bed. So there's WAM process, which is wire arc additive. That's basically a DED process. And there's other things that were, when I joined Relativity Space, I was employee number 20. So the company was very, very small. And so there were lots of things to do and lots of, not enough time to do them all. So part of the stuff that I was working on was just finding out about everything, even things that are not suitable for the company to use at that time, but could be in the future. So doing a lot of that discovery led to other DED processes, whether they're laser DED or laser wire or hybrid arc or EB with wire, that kind of thing. So we looked at a whole range of different things. And how I came to join Trumpf was during the pandemic. There was, not nobody really knew what was going on at the time. A lot of people got sent home, and then you were working from home, and then it kind of got a bit difficult for me because I worked so closely with suppliers, and I couldn't visit anybody, but I couldn't visit my suppliers, which made me really sad. So I looked around for a job where I could still stay involved in the additive space, but that I could work from home. And Trumpf had a lot of positions that were doing hybrid, remote, and or in the office or whatever. And so this position was one of them, and it just worked out really well. I knew them. I knew they were, one of the world leaders in laser technology. And I think that's a cool thing about Trumpf, which not a lot of other let's say powder bed machine manufacturers do, is they actually manufacture their own laser sources. A lot of other people just buy them in and integrate them into, let's say, just say a box. Well, Trumpf doesn't do that. Laser technology is their bread and butter. So I really like that. I knew the name from a long time ago when I was back in UK. And I had this idea of them as being like a world leader, the Rolls Royce, let's say, of the laser world. And I think it's a fairly true statement. Like, I'm not just saying that because I'm an employee now, but I do think that is a huge benefit when you can sort of draw from 50,000 employees and people who are the equivalent of like Nobel Prize laureates in their laser physics field developing all this stuff. You really can't beat that.
And so do you want to talk a little bit about the Trumpf business as it pertains to additive manufacturing? Kind of what are the product lines, or kind of what sorts of offerings on the machine side do you have, and kind of what kind of customers are using this?
Yeah, totally. So, by the way, I will not be attending Form Next, but my co-workers will. So if you're at Form Next, Trumpf will have a booth, so you can come up to them and ask them any questions. But yeah, basically they took it, like a lot of the techniques and know-how and things that they learned from the traditional laser cutting and welding. So I don't want to say laser welding is traditional, but it is compared to the 3D printing world. And so they just translated that know-how into, just say like a box type of thing. So from the powder bed side, they have the TruePrint series. So it varies from a very small sort of build volume, which is based on a round build plate rather than a round corner square. So the smallest one is the TruePrint 1000, and that's very suitable R&D machine, or for people who are just getting started, or even people like, say, dental labs and things like that only need to build sort of small things on a small scale, because the build plate is only 100 millimeters diameter. So it's kind of small, but what it also means is that it's flexible. So if you want to change materials, that's possible. And it goes all the way from the 2000, which is then a 200 millimeter build plate. That's also very suitable for the dental industry. We're seeing a lot of interest in that machine. Then the 3000, and then the 5000. So just leading up to like a bigger size. One of the things that I like about the Trumpf machines is that it is a round build plate, which you don't see very often. And so that means that, you're utilizing more of the build plate. You don't have to worry about dead areas where there's like a fastener and that kind of thing. And then on the DED side, we have just the laser optics. So if you want to buy just the laser, we'll sell you just the laser. And that also can be integrated into a box, as it were. So there's the True Laser 3000, which you might have seen some video that I shared of us printing some 718 blown powder DED, or LMD, as we call it at Trumpf, laser metal deposition. And that can also go on like one of the big machines. So that's a 7040, that's 4 meters long. That is actually based on equipment that's used in the sheet metal cutting world. But if you wanted to, you could mount that on a gantry or a robot, and then just use that whole area to do your build up. So, I think that that's a good flexibility to be able to offer powder bed and DED. and not a lot of other people do that. And then one neat feature that I really like about Trumpf's offerings in the additive world is the availability of a green laser. And now this is very exciting for me because most of the traditional laser AM that we see is using an infrared laser. So infrared is at the wavelength that, you know, the human eye can't see. So 1030 to 1063 nanometers, so in that range. Versus if you were to use a green laser, so that's in the visible wavelength of light, so that's at 515 nanometers. There's also blue lasers at even shorter wavelength, but Trumpf developed the green laser technology from cutting and welding of copper sheet metal. So again, they've taken that and translated that from the sheet metal world into the 3D printing world. And what they discovered is that for very highly reflective materials like copper, aluminium, and then precious metals like gold, silver, platinum, rose gold even. So a lot more of the laser light can be used on these highly reflective materials. So what happens is if you're using an IR laser and you're trying to strike and melt a particle or a piece of metal, which is highly reflective, a lot of that laser light could be bounced off. It's just because of the interaction of the highly reflective nature of the metal. So the laser basically has a harder time coupling to the metal itself, right? And so if you used a green laser or something with a shorter wavelength, the metal is able to absorb more of that laser light. And so you have less scattering, less reflective losses. And that means that more of the energy from the beam is going into the metal. So that will result in 3D printed density that's higher. You have less spatter, a more stable melt pool, and then the productivity therefore should also go up as well because you're able to print faster. You don't need to power through a whole bunch of IR laser power to get that initial coupling of the metal there. And so what that should also translate to, and I would love to do a study on this, by the way, is wear and tear on the machine itself. You know, not having destroyed, you know, scanners or, you know, having to clean down the inside of the machine. I only know from anecdotal evidence, but I would love to do a comparison just to see what the life of things like, how does it affect recoater blades, or do particles, you know, end up blocking gas flow? I don't know the answer to those things, but I can see that that is a huge advantage.
That's really interesting. I think that unlocks a whole new area of discovery of applications with different features and focusing on the laser. And so you have this awesome career path where you've been in a material supplier, you've been an end user, and now you're in the machine manufacturing side. Kind of one takeaway from all of those experiences that you might want to share with others that are kind of in the space of exploring additive careers.
My main takeaway is that in all those job functions and whatever side of the supply chain you're from, everybody wants to do their best work. Everybody wants to make a sale. Everybody wants to receive good material or good parts. So everyone's trying to achieve these things, you know, ultimately to achieve the same goal, to get good material, get good printed parts. What I think is lacking is understanding and empathy from each other's position. So if you're a customer, you want that material on your dock yesterday. You don't want to wait 35 weeks lead time for sheet to end up on your dock. You know, if you are an end user and you order a machine, you don't want to wait 6 months for it to be delivered. You want someone to bring it to you, maybe fly in an Antonov and then bring it to you and install it. And I want to be able to press a button and make sure. That's actually not how it works. You know, there's very few things that are just like plug and play. I think we are so used to instant gratification. And so what I've learned is also to be successful, you have to actually work at it. You have to actually go through a few iterations until you get to a point of, yes, this is a stable process. This is working for me. This material is really good. This is what I like. This is doing the job for me, or something like that. So my I guess a long-winded way of saying, or my point is, I wish we would have empathy for each other to know what that person's going through. Yes, I really want to supply you a machine, but I don't have or I'm waiting on parts, or I can't ship you that material because I have a backlog here, and there are other people who handed in their orders 2 years before you did. And so I would like to help you. And so that my point is, that's what I think. If we had more empathy for each other, we would understand each other's position in the supply chain, and we would be less likely to fight against each other. I think the cooperation is really what I enjoy.
And so, switching notes a little bit, you also contribute to the industry in a lot of other ways. You're a volunteer on SME, and as I wanted to highlight the TIPE Conference as well. So, do you want to speak to a little bit of both of those elements and kind of share some of the efforts going on that front?
Yeah, I mean, I'm involved in Women in 3D Printing. I am very impressed that the additive industry is actually one where women in particular can become leaders, entrepreneurs, business owners, designers. It's let's say if I wanted to open a company making aircraft parts, it may be more prohibitive for me to buy a 500-ton forging press and then start cranking parts out, than if I started with, at least 3D printing, metal AM equipment, laser powder bed fusion machine, or something like that. And so I think that possibility, because you don't need that level of capex, you don't need that level of capitalization, let's say, it's a lot easier for you to do that. And it's mind-blowing why no one has thought of this before. Women in 3D printing is an amazing organization that helps women and girls, or anybody, however you identify, to achieve those goals. So whether you're interested in just education or hobbies or crafts, you might go to maker fairs and want to 3D print your own cosplay items and things like that, or you want to know how to go forwards with this technology as your career. There are so many options, and there are so many people to talk to that can give you help and advice. And I've never seen, or I should say, I've only seen people being supportive in this organization. So I'm very impressed with that. And then I was chosen as TCT Women in 3D Printing Innovator of the Year earlier this year. So I traveled to Birmingham, UK for that. And that was, I couldn't believe it. I really don't even know how I got nominated, to be honest, but that blew my mind. And people told me, well, it's because there's so much you do, like all the things that you do. And I'm like, I don't know, but you don't recognize all the stuff that you've done yourself because you're doing it every day. And then that's another thing that I like to do, is just encourage people. During the pandemic, you would not believe the amount of people that reached out to me and asked me questions about jobs in AM, or how do I work in the space exploration industry, or how do I get a job at Relativity Space, or any of those things. And it was incredible to me that, we have this medium where people can reach you and they would never have met you before, and to varying degrees of success. Some people, achieved their goals, and some people said, hey, that's not for me. But they looked at it and they did that self-examination, and that was mind-blowing. And so I feel like if you can help anybody like on their journey, that's more rewarding than getting a prize. Although I did enjoy getting my prize.
That's awesome. So very much well deserved, and all the work that you do to help support others in the industry is very much appreciated by everyone in the space, and look forward to seeing you at future events in 2023. And so I want to thank you for sharing your career story today and inspiring others to kind of explore the world of additive and all the different opportunities that it can offer. So thank you for joining.
Thanks, Mike. And just on one final note, I won't be at Formnext, but I will be at the TIPE Conference coming up soon here in January. That's a virtual conference where I think almost all of the speakers will be female or identify as female. So if you want to join that, just make sure that you look up TIPE Conference and then make a note in your diary to join that virtually. And there will be sessions from all over the world. So whatever time zone you're in, there will be a session for you to join and take part in. And we love to hear your comments and feedback, and ask us questions, ask any of us questions about careers or advice in 3D printing and additive, because there's so much to offer and there's so much for you to benefit from as an individual, and how you can contribute to the industry. It's incredible.
Absolutely. It's an awesome event. And so I encourage everyone to check that out.